Okay, guys, today we're going to be on lesson 9-7, but this is going to be part 2 of the lesson because we already did part 1, which was finding the points of discontinuity. Today, we're going to mostly focus on the asymptotes of rational functions, so that means we're going to be a little bit more detailed with finding the vertical and the horizontal asymptotes, okay? Now, there's these little inserts right here of this. If we were in class, I would have printed this out for you and you guys would have cut them out and used them while you guys were doing your homework for this. So let's go ahead and read this carefully. So the graph of rational function, right? P of x over q of x. This is obviously a rational function because it's a fraction. You are going to have a vertical asymptote when P and Q have no common zeros. Okay, so they cannot have a common zero. Every single time it's not a common zero, then you can go ahead and think of it as a vertical asymptote. Now, if you do have a factor, right, so x minus a and x minus a, now one thing that is different in these is the exponent. Then that's going to be m is less than n. Then the function f of x has a vertical asymptote where x equals to a. Okay, so let's go ahead and do this. So in other words, if a rational function has a non-removable discontinuity at x equals to a, you will have a vertical asymptote. Okay, so we're going to be finding vertical asymptotes. We want to know, what are the vertical asymptotes, what is the domain, and how does a vertical asymptote relate to domain? Okay, so we're looking at example A, okay? We have x plus 1 over x minus 2, x minus 3. Well, my first thing is, do they have a common zero? No, we don't, right? Because x plus 1, right here, do I have that in the denominator? No, because here I have an x minus 2, and over here an x minus 3. Now, do I have an x minus 2 and x minus 3 in the numerator? No, I do not. Right, so x minus 2 and x minus 3, these are my zeros of the denominator. And neither are zeros of the numerator. Okay, therefore, those 3 little dots mean therefore, x minus 2 and x minus 3 are vertical asymptotes. So you can go ahead and do x minus 2 equals to 0, x minus 3 equals to 0. You add the 2, x equals to 2, add the 3, x equals to 3. So that means that these two are going to be considered my vertical asymptotes, right? Therefore, if they're considered asymptotes, they're going to be considered non-removable discontinuities. Now, the reason why these are non-removable discontinuities, guys, is because they're asymptotes. Asymptotes, you cannot take them away at all. They're going to be there permanently forever and ever and ever. So therefore, they have to be considered non-removable. Okay? So those two right there are your vertical asymptotes. Now, the next question says, how does a vertical asymptote relate to the domain? Or how do I find the domain? Well, the domain is going to be all real numbers except where you have a discontinuity, right? So since these right here are non-removable, that means it's non-removable discontinuities. Okay, so that means that my domain is going to be all real numbers This is my domain. Okay, all real numbers except when x equals to 2 and x equals to 3. Why? Because you're going to go from left to right, but where you have an x equals to 2, you're going to have an asymptote. And when x equals to 3, you're going to have another asymptote, right? So you can have a graph 1, 2, 3. And when you graph this, you're going to have asymptotes there. That means that at that point, you cannot have anything. So therefore, the real numbers are going to be when x cannot equal to 2 nor 3. And your domain is always gonna depend on the vertical asymptotes. So if you know you have a vertical asymptote, then those have to be your restrictions when you're talking about the domain. Okay, so now let's go ahead and move on to example number 2. So I'm looking at x plus 3 over x minus 4 times x plus 3. Now, one thing here that I do notice is that I have an x plus 3 in my denominator, which is also the same as the x plus 3 in my numerator. So if we were to, let's say, cancel out my common factors, then this would be canceled out, right? So what that means is since the x plus 3 is able to cancel out, it will be considered a removable discontinuity. Now, why is it a removable discontinuity? Now, why is it a removable discontinuity? Because you literally moved it out of the equation. You took it out, right? So that means that x plus 3 is a removable discontinuity because you took it out. Now, was I able to take out this x minus 4 right here? No. Since I was not able to take it out and it is in the denominator, okay, these things are in the denominators, then this will be considered a vertical asymptote. So x minus 4 is in the denominator and not a common factor. It will be a vertical asymptote. Okay, so x minus 4, okay, is going to be my vertical asymptote. Why? Because it's in the denominator, okay, and it was not canceled out. So therefore, x minus 4 will be a vertical asymptote that cannot be removed. So therefore, it will be a non-removable discontinuity, okay? So I would get the x minus 4, set it equal to 0, to add that 4. So x is going to equal to 4, and that right there will be my vertical asymptote and non-removable discontinuity. Whereas the x plus 3 equals to 0 will be considered your removable discontinuity. But it will not be considered a vertical asymptote, so just keep that in mind. So therefore, my domain is going to be all x values such that x cannot equal to 4 and x cannot equal to -3. Now, why am I still considering the -3 here? Why am I mentioning this -3 at all? Because it's still a discontinuity, right? And it's still a discontinuity. So it doesn't matter. Yes, one is an asymptote, the other one is not. But at the end of the day, it doesn't matter. The domain is still going to be considered both of them because they're both discontinuities. And that means here that I'm going to have a whole versus an asymptote, but still, it's still going to be discontinuous. So you have to mention both of them right there. Now, again, this part right here, I would have printed it out and have you guys cut it out and put it in your notebooks to make sure you copy this, because you are going to have to refer to this when finding the horizontal asymptotes, because it gives you important information with regards to this. So for horizontal asymptotes, you need to compare the degree of the numerator m and the denominator n. Right? Now remember, what does the word degree mean? Well, the word degree means the exponent, or you guys can also call it the power. Okay, so we're going to be comparing the highest degrees, and then depending on what rule we get, then it's going to tell us what it is, right? So here, for the first one, we have if the numerator degree is less than the denominator, then you will have a horizontal asymptote at y equals to 0. Okay, which is on the x-axis. Now, if the numerator, the degree in the numerator is greater than the degree in the denominator, you will have no horizontal asymptote. Now, if the exponents match, then your horizontal asymptote is going to be on y equals a over b, where a is the coefficient of the term of the greatest degree in the numerator, and b is the coefficient of the term in the greatest degree in the denominator. Now, I know that may seem like a lot of mumbo jumbo, but we're going to go ahead and talk about it right now. I have 3 examples for you that represent these 3 situations. Okay, so we want to know, what are the horizontal asymptotes of the rational functions? Well, what's the first step? To look at the highest degree. So, steps. 1, look at the highest degree. In numerator and denominator. Okay, so we're going to go ahead and look at the highest degree in the numerator and the denominator. Now here, for the first example, I have y equals 2x over x minus 3. Now, do you see an exponent here? Not really, but there is one. Okay, this 2x has a power of 1, and then this x minus 3 has a power of 1. Right? So that means that my highest degree here is 1. So this one has a degree of 1. And then the denominator also has a degree of 1. So that means that here they are the same. Okay? So after I do that, my second step would be to evaluate according to the chart above. To the chart above. Okay? So that means that if they are the same, okay, they are the same, which one is that one going to be? It is this one. If m equals to n, then you are going to get the coefficient y equals a over b, where the coefficient of the greatest degree and the coefficient of the greatest degree in the denominator. Okay, well, what's my coefficient? My coefficient is 2, and my coefficient in my denominator is the one in front of x. Now, I know x right now doesn't have a number, so we just put a 1. Okay, so what's my coefficient? In my numerator is 2. The coefficient in my denominator is 1. So that means that I'm going to get y equals a over b, where a is 2 and b is 1. So what's 2 divided by 1? It is 2. So where is my horizontal asymptote? My horizontal asymptote is at y equals to 2. Voila. And that is how you implement this third rule right there. Okay, now moving on to example number 2. Okay, well, let's look at the highest degrees. I have a highest degree of 1 and a highest degree of 2. So here I'm going to have a degree of 1 over a degree of 2, right? Because I have a degree of 1 and a degree of 2. So just very quickly, so for example number 1, it's m equals 2n, right? Which is number 3. Now here, I'm going to have m equal to 1 and n equal to 2. So that means that 1 is less than 2, okay? So what is that property, or m is less than n? That is going to be the first one right here. Okay, so that means that if m is less than n, which is right here, then my horizontal asymptote is going to be at y equals to 0. So my horizontal asymptote here is at y equals to 0. And that will always be the case when m is less than n. Okay, now let's go ahead and do the third example. Okay, well here my degree is 2 over the degree of 1 right here. Okay, so that means that m is 2, n is 1, so 2 is greater than 1, so m is greater than n. Well, what is m is greater than n? That would be the second rule right here. M is greater than n, so there are no horizontal asymptotes. So here, for the horizontal asymptote, we would say no HA. Okay? And that will always be true when m is greater than n. Okay? And that will be all for today's lesson. If you guys have any questions, let me know.